Welcome back. So, we have a really great clip today. We found one from Roger Penrose from a couple of years ago, and he talks about the Big Bang and the sequential theory that he's made, and also about the speed of light and how time stops. And he kind of summarizes so much of his work for the last decades. It's super interesting. So, we're going to make a commentary video today, first time, and yeah, just going to start with him.
The common view about the beginning of the universe is that it started with the Big Bang, and this is certainly a view which I've held for a long time. And the question raised is what happened before the Big Bang, and the usual answer to that question is, well, the notion of before involves a notion of time, and there wasn't any time notion before the universe was there, so it's a meaningless question.
So Roger Penrose is 87 years old now and a mathematician from Oxford University in Britain. And he's just warming up very gently here to start laying out his own theory with commenting on kind of the current held view and what the normal theory is of the Big Bang and beginning.
And that's the sort of response I would have given. Until recently, when I say recently, this is within the last decade and a half.
So 15 years recently for an 87-year-old person.
I've come to the view that there was something before the Big Bang. My current view is that, yes, there was a Big Bang. It's not like the old steady-state theory, where the universe just was more or less the same, and new material was created all the time, and then it expanded, and new material came. That's not the view. The view is that the universe had this phase called the Big Bang, and then it's expanded, and it goes on expanding, and it's now indulging in this what's called the exponential expansion, which is caused by what people call dark energy. Now,
it's funny to see his face when he says dark energy. He's made statements before. He doesn't like the term like dark energy because it's not dark, it's transparent, and it's hard to understand the nature of it. So he's one of those kind of original thinkers, and he is relabeling many of the terms that are most commonly used.
It's actually the case that in 1917, 2 years after Einstein introduced his general theory of relativity, he put in a term into the equations, an extra little piece, which was called the cosmological constant. Now, he introduced this in order to have a universe which was static. And he knew that by putting this extra term in, the cosmological constant, he could have a model of the universe which stayed the same all the time, which is what he wanted.
So it's interesting watching this because he's kind of a master of cosmology. So he's going through the established history of the evolution of the different theories, like he's kind of a mastery feeling to it.
However, he realized this was a mistake because the universe was observed to be expanding, and when he clearly took that on board, he rejected his cosmological constant. However, it turns out that he was right all along, in that this term that he introduced has an effect which causes what we see now as this extra expansion that the universe is doing. It's sort of expansion slowed down, and then it started to increase.
Okay, so we're going to skip a bit into the video. So he goes through more of the basics, and then he starts talking about the black holes and how Stephen Hawking discovered that they're actually emitting a little bit of energy, a bit of radiation. So the black holes are kind of leaking a little bit, and then, or you can also think in the very long term that they're evaporating slowly. So he goes through things here, like the next few minutes, how in the long future there will be no matter left, and there will only be radiation and photons, and then he has some more theories about what comes then. So if you jump to around 840, this is going to be a very boring universe when there's nothing left except photons.
All of the universe's lifetime would be such a boring state of affairs. But then I began to think, well, who's going to be bored by this universe? Not us. We'll be long gone. The things that are around will be photons. And photons are very difficult to bore, partly because they probably don't feel anything, but that's not the point.
he's also very humorous. And there's one other comment to that, like photons don't have feelings. That one other part of his work is about consciousness and quantum physics, quantum mechanics, and consciousness, and yeah, some ideas about how this emerged at some point due to physics on an elementary particle level.
The point is that photons don't experience the passage of time. That's because they go with the speed of light.
And this is what we've been talking about for the last few episodes, or like clips here, that how does things look from the tip of the light beam when there's no time, there's no space, but it's still going across the universe, like 300,000 kilometers a second.
And because of the effects of relativity, the clock moving with us faster and faster, closer to the speed of light, slows down. If it reaches the speed of light, it doesn't register any time at all. So as far as that photon is concerned, right out to infinity is no time at all.
So it's basically a frozen universe in some sense.
So then I began to think, well, what happens to this world? And because of ideas that I've been playing with a lot when people were interested in the energy in stars running around each other and black.
It's so nice. He spends so many minutes just warming up to his kind of main hypothesis here, establishing the common physics and then adding bit by bit up to his own ideas here.
And so on. How do you measure the energy radiated? And the way to think about this was to go all the way out to infinity. And you can do a little trick, which is a mathematical trick. You can squash infinity down. Maybe some people will have seen these Escher pictures where you see angels and devils interlocking, and you see as they get round to this boundary, which is a circle, they seem to get smaller and smaller and smaller right down to the edge. But as far as those angels and devils are concerned, they're all the same size as each other. But they're squashed down in a way which they're squashed in all directions by the same amount, and then the boundary represents their infinity. But
just two things here. First of all, Escher is a very interesting artist. He has all these drawings, illustrations, which are often like a mind bender, like the perspectives are twisted, so you have these people going around in circles forever, like on the stairs, for example. So that's one thing. And the other is that the mathematical trick of transformation is something that you will be used to in mathematics, that you can do. For example, you can have an equation that's not possible to solve, but then you transform it into another kind of dimension, and then you can do simple mathematics on it, and then you transform it back, and you have the solution. And we're not sure how it works, but it's consistent and it follows logic. But many parts of mathematics are already like this, so that's why he's applying this now to physics, and then like at this end state of kind of an infinite, like, how to transform it into a finite space in some sense.
you can see the boundary, it's just there. And if you had a kind of geometry which didn't know distances, but only knows shapes and angles, then infinity you can represent in this finite way. So I'm taking the view that our universe is very much like that. The remote future is just a boundary, and that things which have no mass, have no way of telling their size, they have no way of measuring time, that is the boundary they reach. Now this is a crazy thought, but the idea is that that's what our universe is like. And when there's nothing...
So funny how he's one of the oldest active people in cosmology, but he still hedges when he says like it's a crazy idea.
Thing around, such as photons, which have no mass and therefore they can't keep time, their infinity is that boundary. Then you can ask what's on the other side of the boundary. And what I'm saying is what's on the other side is the Big Bang of another eon.
So eon is his term for the length of a universe, when you have several like sequential ones. It's the whole lifespan of the universe. So here comes his thought that represents the boundary point where you get a rebirth of a new one.
Now you might say, well, why doesn't the Big Bang know where it is, if you like. The answer there is similar, but the opposite in a sense. When you get near the Big Bang, the temperature gets hotter and hotter and hotter. The energies get bigger and bigger and bigger. And then the particles which have their mass, which makes them behave like clocks, that mass becomes irrelevant because the energy is so much larger than the energy in their mass, then you can forget it. That is to say, they behave like photons. They behave like particles with no mass. And therefore they don't register this passage of time, they don't register sizes. So the Big Bang doesn't know whether it's big or small, anyway, any more than the remote future knows whether it's big or small. So it makes sense to join them together. Now that's the crazy thought, but it makes mathematical sense. So it means that the remote future of our expanding universe becomes the Big Bang of the next eon.
And now comes to another very interesting part, as we talked about before in the clips on this channel. Like, if this is the case, would we see remnants of the previous universe in our current one, in the kind of the fiber of space, for example? Meaning that, like, space is, well, around us. So, like, in the little space you're holding in your hand there, could there be remnants at the particle level right here in front of us all the time that that shows the early ones? So just listen here.
And our Big Bang was the result of the remote future of an eon prior to ours. And it seems like a crazy idea, but it does lots of things for us. One of the things it does for us is it creates a universe which is very uniform, which is a great
So that's point one. You get a uniform universe, which is what we see.
puzzle why the universe should be so uniform. And it's one of the reasons people introduced inflation. Another thing it does is it produces dark matter. Now you see, this is one of the current mysteries of the universe. Most of the material in the universe seems to be invisible to us. We know that from galactic rotation that there's more mass in galaxies, or almost all galaxies, than we see in stars. And this mass has been very puzzling. You can tell from the orbits of stars that there is more mass around than you see in the actual stars.
So he keeps talking about dark matter and how we are. One possible solution for this, you might think of this a bit of a placeholder. We have different theories, but then, for example, the amount of visible mass in a galaxy doesn't explain fully the physics of it, and kind of the spin is there should be more mass. So then we invent, for example, the term dark matter to make as a placeholder to make the equation still hold, but it's not fully a satisfactory kind of term. So here he is. He builds possible interpretations of this. So that's very nice. And as you can also think of another thing, that like a sequence of universes is also, if you think of just in any species of animal, for example, there is a sequence from the earliest like one-celled animals until it keeps growing and evolving, and then that might also have some kind of implications for the current universe, and kind of this thing that there's so many fine-tuned parameters at the particle level for the universe to function the way it does. And maybe this has been kind of a evolving process over a time span that's impossible to understand, but it's a hypothesis.
And it's been christened dark matter. That's quite different from dark energy. This is dark matter. And dark matter is a kind of matter, but it doesn't seem to fit in with any theory of particle physics.
So just an example of something that's like inheritance almost from a previous universe. Okay, so I would highly recommend watching the whole clip, the whole 20 minutes. It's a short summary of his like the high points or like the essence of much of his work, and he's just brilliant. He and Stephen Hawking have kind of they're onto so deep and fundamental things, and they're also creative with it. So this is Sequential Universes, Stephen Hawking with both the black holes and the gravity as well. Like gravity is the thing that creates action. That's, I think Stephen Hawking called it his bet in one of his videos. Okay, so we're gonna stop there, and hope some of this was interesting. This is really like a good place to start, or to just get some inputs for physics and cosmology. And as always, thank you so much for watching, and have a great day.